So we're in your chemistry book in the last section, 2.5, and we're going to talk more about atomic mass. Remember we had those atomic mass measurements, and when we were talking about atomic mass and that number being the A number, the top number. But now we're going to talk about the atomic mass units and how much the atom actually weighs, or is mass. So as part of his atomic theory, John Dalton developed the concept of measuring the atomic mass of an atom. Can you believe that? Because ordinary mass units such as gram and kilogram are very large, there's no way they could measure an atom, right? So they had to have a new unit. So they called this unit the atomic mass unit, and it's just a U. The atomic mass unit is defined as exactly 1/12 the mass of a carbon and atom, which has 6 protons, 6 neutrons, and 6 electrons. And 1 unit equals approximately 1.6605 times 10 to the negative 24th. We're going to get that in the next chapter, so you'll find out in the next chapter how they figured that out. Because protons and neutrons have almost the same mass, and the mass of an electron is very negligible compared to the masses of the nucleons, the atomic mass measured in atomic mass unit approximately equals the atomic mass number. So a little tiny bit more, right? And this relationship is only approximate because the masses of the protons and neutrons are not exactly equal to 1 unit, and also they have to take in the mass of electron, which is very, very small compared to the proton and neutron. So how did they figure this out? So they measured it by what they called a mass spectrometer. And this mass spectrometer measured that there were heavier neutrons than protons, and how light the electrons, and they used this for measuring. And so the concept of this is a picture here, as you see. So basically, if you have the wind blowing and you have a lighter car, well, the lighter car is going to turn more than the heavier truck, right? And that's how they figured this out with this mass spectrometer. Here's the picture that as they passed the particles through here, the heavier ones didn't turn as much as the lighter ones, right? That's how they figured this out. So the ions of the element to be studied are produced by either bombarding a gaseous sample with an electron beam or ionizing the solid sample with a spark. That's how they did this as they're traveling these ions to figure out which ones are heavier than the other. The fast-moving particles pass through the magnetic field, which deflects them to varying degrees. All ions of the same charge experience the same force from the magnetic field. Instead of wind, we have this magnetic field pushing them, right? It's not really wind pushing them through, it's the magnet. See how here's the magnet, and the magnet bringing forth the lighter as for the ions than the others. So it's a little bit complex, but this is just telling you how they figured out to the mass number, in doing this. So you can just see these two pictures are actually pretty good, telling us this mass spectrometer analogy and how they used it. And here you have, the gas comes in with the electrons, and you have the magnet pulling it, and instead of the wind, and it looks like either this. And so now they can know which beam of the heavier or lighter ions to weigh them. So, pretty neat, huh? Wonder how they figured that out, but they did. So we refer to the atomic mass of an element. We usually mean the average atomic mass of a specified element. So you get all this element, and they want to find the average weight of all of it, because some of them are going to have isotopes, neutrons. Some of them will have extra neutrons, and so they'll be a little heavier. So it depends the percent of the neutrons causing them. And so they go through this average number to find out the average number of, like, if they took, say you took lead of 204, lead of 206, lead 207, and lead 208. These are all the lead. And lead 204 only has 1.4%. Lead 206 has 24%. Lead 207 has 22%. And lead 208 has 52%. So you'd have to figure all this out to find out what that would be the average. Basically, finding the percentages of all these and adding them together to find out what the number is going to be. So if you look on a chart here, let's look at this chart here. We have hydrogen. We have hydrogen here. I hope you can see this pretty well. Push it up a little bit maybe there. Can you see it better? So if we have hydrogen 1, 1, and you have the percentage, 99% are 1, 1. But you have some of them that have extra neutron as 2, 1, and some of them have 3, 1, just very trace. But as you go through this, you'll find out the mass unit would be an average of these when it comes out as averaged to these. Well, this here, of course, would be 99%. How many protons? 1. 0 neutrons. Mass number would be 1. And here is the unit, 1.0078. You got that? And so if you have 2, you're going to have only 0.012 or 1, 2, not very much, but you're going to have 1 proton, 1 neutron, and the mass number being 2. So it's going to be 2.014. So these are different. These are see how the mass unit varies on the amount of, because there's a neutron and a proton, it makes it heavier, okay? So the same with carbon here. So you have carbon, and you have 98% of carbon is carbon 12, but you have some that's carbon 13 and some that's carbon 14 with extra neutrons. So how many protons? 6. How many neutrons? 6. Mass number is 12. Here we have 6 protons. Now we have 7 neutrons, and so the mass number is going to be close to 13, right? Because you have extra neutron. And this is the same. The mass number is going to be 14.0032. This is including, this right here be including the electrons too. Same with fluoride. You have fluoride here. You have the percent. 100% of fluoride is 19. So it would be 9 protons. So 19 minus 9 would be 10 neutrons. Mass number would be 19. And we find that the isotope mass number is close there. It's 18.9984. So this is the exact mass number, the isotope mass number. Copper the same way. We calculated this. The percent is 69%. Would be have this one with the 63. So we have 29 proteins, 34 neutrons, and the mass number is 63, and lo and behold, it's close to 63. And here we have the mass number, the percentage, 30% would be the 65. So we have protons 29, of course, so protons are always going to be 29, neutrons 36, and the mass number would be 65. Yep, it's close to that. You see how they did that? Iodine, 100% of iodine is this, so we have 53 protons, 74 is 127 minus 53, 74 neutrons. We have 127 here, and you see the isotope unit number is 126.9004. It's either a little bit less or a little bit more, depending on the weight. So this is how they found the weight. Here's lead, which is Pb. We have lead with 204 and 206. So the 204 here is, we have 82 protons, 122 neutrons, because you have 204 minus 82, 122 neutrons. 204, the number now is 203.97, close to 204, huh? Now we have lead with 206. We have basically 24% of this is that. Let's move it up there. Move it up. 24, we have 82. See, 82 gives the lead number, which is protons, which are all 82. Neutrons are varying. So we have 124 neutrons, 125 neutrons, and 126 neutrons. And then we have the mass numbers here, all different, 206, 207, and 208. But you look on here, the unit is very close, 207.976, 206. So depending on that addition of the neutrons or how much the electrons added. So to determine those numbers. So these are average. These are all average numbers, okay? So I hope you kind of got this. This one on here just to tell how to do an average, but I'm not going to get in how to do an average. We'll do that when we do the problem. So the average. So let's look at the example here. So see, very few, because you have average atomic mass, very few elements have only one isotope. So when they have more isotopes, you have to take the percentage of all these different isotopes and take that into account to find the average. So that's what they're going to be doing here. And let me show how you do that. Let's see. Calculate the average atomic mass of neon gas if it naturally occurs. 90.48% is 20 over 10, which is 10 means it's 10 protons and 20 means it has 10 neutrons, right? Well, it comes to that unit would be 19.992. It's almost 20, right? And then 27% is 21 over 2 is almost 21 units. And then the other is 9.25% is this. So you have all these percents, but you still have neon. So to find out the average atomic mass, how do we do this? So first, we're going to write the percents as decimal fractions by moving the decimal 2 places to the left and dropping the percent sign. You know how to do that. So the fraction of the atoms will be 19.992 units, 0.9048 units. You're just getting these up here. Let's see. You have 19.92 units. You have the fraction of the atoms having is and you move is 9048. The fraction having the mass of 20 is, and the fraction having the mass of, so basically, here's how we do it. Let me show you here. I'm going to take this off and show you. I wrote it on my own so you can see it better here. But so we have to write them as decimal fractions first. Okay, so the mass of neon gas if naturally occurring is 98.48. So we're going to move it over and we change that mass to 0.9048, right? The next one we change to, it's 19, so we're going to change this to this is going to be 19.992. And then we're going to put this as 0.002. Let me show you how I figured this. I'm not really getting you this very easily. So let's show you how to figure this. Okay, so we have this number. We have the first one is 20 over 10, and that's going to be 19.992 units. And 90% of that, 90.48% is that. And then we have the neon 21 over 10, which is 20.994 units. And then basically that's going to be 0.27% or 27% or less than 0.27 and 9.27, okay? So first you're going to drop the percentage. So you're going to get these numbers here, these percent numbers are going to be 0.9048. This number is going to be 0.0027. And this number is going to be 0.0925. Those are the percent. And then you're going to multiply it by these unit numbers. So these unit numbers are going to be 19.992 and then 20.99. These are the weights of them, but we're going to multiply. So we multiply these, and this is what I got. 18.09 when I multiplied this by the unit, and multiplied this by the unit, and multiplied this by the unit. So these are the numbers I got. 18.09 units, and 0.0057 units, and 2.3. So we added those together, and we got 20.18 units, okay? So that is going to be the addition. So calculate the average atomic mass of these units. If naturally occurring, it's going to be 20 are 20.18 units. And sig figs, you got to make sure you have 4 significant. Actually, it's 1, 2, 3, 4, so at least 4 20.18 units. Okay. Whew. So I hope you got that. So it's not that hard. It's just that I have to. They're using these units, and you have to use your calculator to do this. So let's go on to the next one here. Okay, your questions. The first question says, what unit is usually used to measure atomic mass? Well, we know that, those units. Atomic mass units with the U, right? So what laboratory instrument is used to measure the masses of atoms? We have the mass spectroscopy, right? That thing that we had a picture of. So what type of average is used to calculate average atomic mass? Is the weighted average. They're going to weigh, the weighted is weighing them and averaging them out, the weighted average. Okay? So now here we're going to do this calculation. Calculate the average atom mass of magnesium given the following percent abundance, just like we did before. And we have them all there. I'm not going to go over them. You see them there. They're in your book. And we're going to do that. And then let's work it out. So here we have magnesium is 78.99% magnesium with the 24, and 10% with 25, and 11% with 26, right? That's what we have. And you have those numbers there. And so now what you're going to do basically is you're going to multiply those numbers together. See how I did 7.7899 and multiply those numbers out. And as you multiply these numbers out, you will get basically, and I didn't multiply them, but you're going to multiply them out. And from that multiplication, you'll get, adding them together, you'll get the average weighted average. Let me see. So you multiply them out and then you add them together. I just said how you multiply in here, but I didn't really add them together. But as you add them together, as I have a picture there, you'll get the number. Okay? So lithium. Naturally occurring lithium consists of 7.59% lithium-6, right? And 92% lithium-7. So here's how I did this. So basically, you are going to multiply those together. You're going to multiply them together. Multiply the numbers together, these two numbers together. And then as you do, you're going to add those numbers, then you'll get the answer to that. So you have to do this on your calculator. Okay? Just to show you how you do this. So you may have to do this. If you have to do it on a test, we'll see. But I'll go through them on your quizzes and stuff to show you how to do them. So anyway, that's the end of this chapter.